Cool, thank you. Okay, thanks Nikhil for the kind introduction. And thanks to all the organizers, both here at IIT Bombay and at TIFR, for inviting me to give the memorial lecture and also this tutorial. And also, thanks a lot for the immaculate arrangements. It was delightful to visit both TIFR and IIT Bombay. Okay, cool. So before getting into the thick of the tutorial, I'll just start with a very brief overview of my research lab at CMU. So I lead a research lab which I've named as Thesis Lab because we do research both in theory and in systems. So we build systems and model new theoretical problems based on the real-world challenges that we observe in systems. And then take the insights from the theoretical solutions and modeling and take it back and build state-of-the-art real-world systems. On the theory side, we work on problems in information and coding theory and also probability and statistics. And on the system side, basically we're looking at reliability and performance, especially better tail performance, which again needs resilience, in a variety of different systems. One is in distributed data storage systems, which I'll talk about today in the first half of the tutorial, and also in machine learning systems, which I'll cover a little bit in the second part of the tutorial. And some things that I will not be covering today, but we are actively working on is in content distribution networks and live video streaming. Okay, for today's tutorial, in various parts, I'll be covering some of the works that I did and what my research lab is currently working on. And for those parts, here are the students and the collaborators with whom I've worked with. You will see the students' names and the collaborators' names as I point out some publications. And especially I would like to call out our collaborators, my students and I have had great pleasure of collaborating with these collaborators. The first one is Greg Ganger. He's a faculty at CMU, mainly works on computer systems. And second one, probably most of you would know, Venkat Guruswamy. He works in theoretical computer science and also in information and coding theory. He's a faculty at CMU again. And thirdly, with Shivram, who is a faculty at University of Wisconsin-Madison, who works primarily on computer systems. Okay, so with that, we're all living in the age of data, right? So there is unprecedented rate of growth in the amount of data for various reasons. And new data and performance-hungry applications are popping up every day, right? So self-driving cars, genomics, Internet of Things, and what have you. Now, all these applications are mainly enabled by big data systems or so-called data-driven systems. And these systems mainly store and analyze massive amounts of data. And these systems have this as a foundational layer, large-scale distributed systems, which we come across sometimes in our day-to-day life, and sometimes that we hear about as to what big corporations are using, right? So one of them is data centers and warehouse-scale computing that almost all internet-based services today employ. Right? And also now, a lot of this data storage and computing is moving into the cloud. So it's kind of consolidating, and those systems are getting bigger and bigger. And also, on the other side, there are like truly geographically distributed systems like content distribution networks, which take content from content providers and do delivery to the end users by having systems that various geographical locations and then serve users nearby. So in all these large-scale distributed systems, one thing is common, that is they are prone to non-ideal operating conditions, such as failures, unavailabilities, load imbalance, and so on. And adding redundancy is one of the key ways of providing resilience to such non-ideal conditions. So this could mean in storage systems duplicating data, or in computing systems duplicating in some various forms. Doesn't have to be exactly duplicating, but duplicating queries. Right? However, while redundancy provides resilience, it comes at a cost, right? So it requires additional hardware, so it's directly translating to dollar cost, right? And it also results in increase in other costs associated with it. That is like, you need more physical space, you need more energy, more cooling, more operations, and so on. And hence, it's critical to introduce this redundancy in a resource-efficient manner, right? And in this tutorial, we are going to look at resource-efficient redundancy via coding theoretic tools. So in the first part, I'll look at coded data storage, that is coding theoretic tools to improve distributed data storage systems. And in the second part, we will look at coded computing, that is using coding theoretic tools to provide resource-efficient resilience to distributed computing systems. Now, before going into these parts, I would like to give a quick primer on coding theory in case there is anybody here who is not familiar with coding theory, because soon we will start using the notation and tools from here, in which case you might get lost. So just as a quick know the audience kind of question, so how many of you here are not familiar with coding theory? Okay, so good number. So let me go through this primer. Okay, so I have a sentence here with some characters missing. So can somebody tell me what this sentence is? Louder. Fun ride. Okay, cool. So there were so many characters missing here, right? But still, it worked, right? Most of you could easily read out the sentence. So why did this work? So it's because, you might be feeling shy to answer, but you all know this. This is because of redundancy. English language has built-in redundancy into it. And so there is resilience in it, and we can understand and communicate even if something is missing. And this is what helps us to communicate with people, because we might not hear everything, the accents might be different and so on, but still we can understand, right? Coding theory is basically, in particular like codes specifically, are clever ways of adding such redundancy in order to enable, let's say if you have a sender and a receiver to decode what was sent by the receiver, like similar to how we communicate. So as a general model, we will consider what are called erasure codes. So in this case, we have what is called a message that a sender is sending. And keep in mind that when we are looking at these storage and computing, there's no real communication as such, right? We are not looking at a transmitter or a receiver. So here it's more general, as I will point out a bit later. So you have a message, and that goes through the encoder and encodes this message into what is called a code word. And I'll denote message by M and code word by C, okay? And then this code word goes through what is called a channel. So for example, in storage systems, this channel would be storage. Basically, you store some data, and after some time you read it, and then something could be missing from it. So the channel is the storage medium. Right? So here, message would be the data that we store. So the channel is called an erasure channel because in the tutorial today, we will focus only on a particular type of noise called erasures. So erasures are similar to what we saw in the example in the previous slide where something is just missing. So you know that it is missing, you just don't know what its value is. There is another type of noise, which you all might have seen, is what is called errors, right? So errors where one in the same, if we take the same example as the previous slide, one particular letter might be replaced by another letter. So there won't be anything missing, but there will be some errors, right? So errors are in general harder than erasures, because erasures you know that something is missing. In errors you have to first detect that there is an error, so that requires some cost. But in this tutorial we will focus only on erasures. So from now on you can forget about errors and think only about erasures as the type of noise. Okay, so now this code word goes through this erasure channel, and then it comes out with some erasures, and we will represent it with C prime. Okay, so it may or may not be equal to C, in the sense that there could be or there may not be erasures. And then what the decoder has is just this code word C prime that came out of the channel, and using that it has to decode. So it has to spit out the message that what it thinks is the right message, or declare that it cannot decode. Right? So noise would be erasures, and decoder has to deal with erasures. Okay? So we will use a little bit of additional notation. K would be the length of the message. So think of it like a vector of some symbols. So to start out with, think of it like a vector of bits, right? So you have a certain K length vector of bits. That's your message. And then N would be the length of the code word. Okay, so K would go to N, right? So redundancy means we will add, right? So we are going to increase the length. And then capital C is the code. So what is the code? Code is a set of what is called code words, which are n length vectors. Yeah. Yeah, so that's a very good question. So the question is whether erasures at one position is independent of the other. So that may or may not be true. So that all depends on what kind of channel we are dealing with. So if the channel is independent across locations, then it is independent, but it could be dependent too. Right? So in the problems that we will look at today, it doesn't matter so much because we will not be looking at dependence or independence in that kind of probabilistic way. We will be looking at kind of worst case guarantees that even if so many erasures happen, you are resilient. Yeah. But in order to decide on what parameters to use and how many erasures you want to tolerate, one would have to think about what the channel is, and if it is correlated, then more erasures can happen, and so on. Yes, it matters, but today we need not consider it. Any other questions? So by the way, feel free to stop at any time if you have questions. So this is a tutorial, so I want to make sure you all understand the material. So I don't want to just run through the material, okay? Okay, so capital C is the code, which is basically a set of vectors of length n. We are going to call them as code words, right? Set of code words. For each message, there will be one code word, right? And whenever you want to transmit or store or do something with a message, we will send, transmit or store the corresponding code word. And since we are adding redundancy, it's going to provide us resilience against this channel that the stored code word or the computing code word will go through. Okay, so is this model clear? Any questions on this? Okay, good. So I'll take a quick example, right? So let's say, so there is a very popular class, of course, very simple code called single parity check code, okay? So let's take this example, and here, K, is this visible? No, right? Okay. Okay, let me do this. Okay, so let me take K equal to 2 and N equal to 3, and single check A single parity check code is, in this case, is just we'll have, let's say, 2 message bits, that is k is 2, so length 2 vector, and 1 parity check, which is basically in this particular code, is just XOR of the message bits, okay? So we'll have M0 XOR M1. Thank you, yeah. Okay, so quickly, right? So if I have message 0, 0, this is going to be my code word, which is length 3 because n is 3, right? So what would be this? 0, right? So, and if my message is 0, 1, this is going to be 1, 1, 0 is 1, and 1, 1 is 0, right? So these 4 vectors are my code words. And these 4 code words together is our code. And whenever we want to transmit, so I'll just say transmit when talking in general, but when it is transmit, think that it could be like storage or any other channel application. So whenever I want to transmit message 0, 0, I'm going to transmit 0, 0, 0 with this entire code word, right? So these are my 4 code words. Okay, so now for this code, an intuitive way is to visualize this. In general, not just this, any binary code, and also can be extended to other alphabets, is to visualize these code words as nodes in this hypercube. Okay, so we have n equal to 3, so shown here this 3-dimensional hypercube, and the blue nodes, the shaded nodes, are our code words, right? So since n is 3, the total number of nodes that are there is 8, but out of that, we are choosing only 4 of them, right? So the rest 4 are not used as the code words. So if you think about it, if we use all the nodes as code words, then can we get any resilience? No, because then you don't know when something is transmitted, and if something is missing, you won't be able to decode. For example, if 110 is there, so I have 110 in the code, in my code, right? If I also had 111 in the code book, right? So then suppose this gets erased. Right? That is, the last position gets erased, right? So in this code, then there would be no way for the receiver to know whether it was 110 or 111, right? So just because I have only 110 in it, we can distinguish between these two. So in general, basically, out of all possible vectors, code design is choosing some subset of those vectors so that they have some good properties, and that provides resilience. So one of the things to observe here is that there is some distance between these vectors chosen, right? So similar to this, 110 and 111 are adjacent nodes in this hypercube, right? And if you observe, no adjacent nodes are chosen in the code, right? So no 2 adjacent nodes are code words. So if 2 adjacent nodes are code words, then we'll have the same problem that we saw in this example, right? So there has to be some distance between the vectors that is distance between vectors in the code, which is basically distance between the code words. And this distance has an intimate relationship with the resilience that the code provides. So there are beautiful results on this. We will not go into it today in the interest of time, but basically given what is called minimum distance, which is the distance between 2 closest code words in the code, you can say what is the maximum number of errors or erasures that can be tolerated. Okay, so just to keep in mind that this distance matters, and it's an important metric for the code. Okay, so now in general, we have been referring to symbols as bits, but symbols may come from other what are called alphabets. So we'll use the notation sigma to denote this alphabet. So this is just to understand what a code is. We will not be using sigma later in the talk. So sigma is the alphabet, and Q is used to denote the size of this alphabet. Okay? And code is going to be a subset of all possible vectors, as we just saw, of vectors of length n, where each position comes from this alphabet sigma. Right? So maybe let me ask this example a little bit later, or it might come a little bit later, but let me ask here. So in the code that we just saw here, what was the alphabet that we used? 0, 1, right, which is the binary alphabet. And here the size is 2, right? So for erasure codes, we need alphabets to have some properties so that we can do some math with it, right? And mainly what we want to do is to solve linear system of equations. So why? Because typically what you will have is code word like this and equations like this, and you know what different positions are as a function of the message symbols, and then you will have some of them and you will not have some of them. And basically you have to solve these equations in order to find out what the message symbols are. So basically we want to do linear system of equations, and for that we have to be able to do addition and multiplication and inverse operations like subtraction and division. Right? So typically the sets over which codes are designed are finite, and these are called finite fields, as we'll see. And this is where the question that I had comes in, but we have already answered that. Okay, so often only binary alphabet is insufficient. Again, there is beautiful theory behind it, and as I was talking about distance, we will not be able to design codes with certain kind of properties with respect to distance if we limit ourselves to binary alphabets. So often we need alphabets of larger size. And as I mentioned, typically we use finite sized alphabets, and these are called finite fields. Okay? They have certain properties, and we won't have time to go in depth into that. But for the purposes of this tutorial, you can consider a finite field as, for this prime q, zq. That is basically the set 0 to q minus 1 with addition and multiplication modulo this q. So as long as q is prime, for this set we will be able to do addition, subtraction, multiplication, and division, like both inverse operations for addition and subtraction. Okay. So now let's look at erasure correction capabilities for a particular code. So here is an important theorem that we will kind of keep referring to at various points in this tutorial. So for any nk code, it can correct at most n minus k erasures, right? So intuitively, we are adding only n minus k additional symbols, right? So given that we want to be able to handle all possible message vectors, intuitively you can see that we can kind of handle only n minus k, at most n minus k erasures, right? And codes that meet this bound are called maximum distance separable, or MDS for short. Okay, so MDS codes, basically an nk MDS code can tolerate any n minus k erasures. So MDS codes achieve maximum possible erasure correction capability, or in other words, for a given code and the amount of erasure correction capability a code provides, it requires minimum overhead, so vice versa. A popular MDS code that we will see at various points in the tutorial today, and also widely used in practice, is called Reed-Solomon codes. Okay, so in various applications, including communication, storage, and computing, Reed-Solomon codes are widely used. Okay, so we'll just take a very, very brief look at what Reed-Solomon codes are, because we will come back at later point in the tutorial. So let's say we have this message where we have k symbols, a0 to ak minus 1, which come from a finite field. Consider this polynomial, which is of degree k minus 1, which is constructed using these message symbols as the coefficients. So you see these message symbols ai, a subscript I, are the coefficients, and x is the variable for the polynomial. Okay? Now, Reed-Solomon code is very simple. So the code word for Reed-Solomon code just picks n distinct elements from the field. Here it's just 1 to n, and then evaluates this polynomial at these locations. Okay, so this is it. This is the code word, and this is the Reed-Solomon code. So one thing is that we want to have this I to be distinct for each of these locations, P of I. So we need the field size to be at least n. Right? So this is one way you'll see that we need field higher than binary field, right? So you need a larger field, larger sized alphabet. Okay, so now we have the code. Let's see how it helps in recovering erasures, right? So suppose, now I told you earlier that Reed-Solomon codes are MDS, and we know that MDS codes can tolerate any n minus k erasures, right? So basically, in order to see that, what we will have at the decoder is basically some locations of this n length code word missing, right? So which is basically at most n minus k missing. So you will have k, at least k of these evaluations of this polynomial, right? So what was the degree of this polynomial? K minus 1, right? And we'll have at least k evaluations. And there is a very important and fundamental theorem about polynomials, and you might recall from your math classes, that given any k points, xi and yi, there is exactly one and only one polynomial that goes through these points, which is of degree k minus 1, that exactly matches these k points. Right? And you can actually easily find this polynomial using interpolation. So you might have heard about Lagrange interpolation, or there are other ways of interpolating. But basically, given k points for k minus 1 degree polynomial, it is exactly determinable. So we can find that, right? And in this case, once we find the polynomial, we can find we have the code word. And in all codes, once you know the code word, you can easily map it back to the message. Okay, so this is it. So Reed-Solomon codes are basically based on polynomials, and you use the fact that what is its degree, and you'll have at least so many evaluations, and you can decode and find the polynomial. Okay, so now that we have had this primer on coding theory, so let's move into the first part, which is on storage. So here I'll briefly have to switch to another deck of slides. Because of the size, it doesn't fit into the same presentation. Okay. Okay, this got closed. Okay. Okay, cool. So we will get into the first part, which is on storage systems. Okay, so here is going to be the broad outline for the part 1. So I'll start with an introduction to distributed data storage and kind of explain how coding theory comes in there. And I'll talk about two problems. One is what is called reconstruction problem. So two problems related to codes for storage. One is reconstruction problem, which is a very well-studied problem, and there has been numerous works, including my own. And there are two specific sub-problems within that. One is about bandwidth, and another one is about degree. I'll go into that briefly and explain how actually works in coding theory have had real-world impact in this problem. Right, so this part is going to be brief because there has already been a lot of work. But it's important because it's highly motivating to see how works in coding theory have had made real-world impact in this realm of distributed storage. Of course, coding theory has had real-world impact, significant impact, in fact, in the communication domain, right? And then I'll talk about a relatively new problem, which we're calling as code conversion problem, which is quite new, and there is a lot of things to be explored, so I'll delve more in detail on that. And it also has significant potential for real-world impact like this reconstruction problem. And if you had attended my talk at TIFR, so there will be some overlap in the code conversion problem part, but it's a good time because now it's a revision for you and you have to ask questions, okay? So I'll be looking at people who are there at the talk and you have to ask questions. Okay, so let's start with the introduction. So basically, data-driven systems have this kind of a stack where there is typically a storage layer, which is like a distributed data storage system which stores all the data. And typically, nobody ever deletes the data because they want to store all the data. Who knows, maybe in the future, you might want to find some information from it, right? And then on top of it, there's typically an in-memory caching layer, which helps so that then applications don't have to come back to disk every time because hard disks have high latency of access. So typically there is an in-memory caching layer. And then there is what is called an execution layer, which executes the tasks which the application layer sends to it. And then on top of it, there is application layer of various kinds. There are some interactive applications where people want very quick responses. There are what are called batch jobs, which run over a long time, like a background job, and so on. But as you can see, storage layer is the foundational layer for these data-driven systems. And they kind of serve as a repository for all the data in the universe for many of these enterprises, right? And hence, they are typically really large scale. And the size can run into hundreds of thousands to even millions of disks. And the amount of data stored in just some of single enterprises today, because of this consolidation towards the cloud, and also some single enterprises just have a lot of data, it can run into exabytes. Exabytes is 10 to the 18 bytes of data, okay? And then these are stored across hard disks, and since multiple hard disks can be put into a single server, these are spread across like multiple thousands of servers. And these are interconnected via a data center network. So disks can communicate with each other, and I'll go a little bit detail later that it's not, so it's kind of an hierarchical network structure. So in such a large-scale distributed storage system, let's look at what are the key resources, because we want to keep that in mind when we are trying to optimize, right? So the first thing is storage space. So this, as we discussed earlier, very briefly, that directly relates to the cost of the systems because it is hardware cost. And sometimes, given that storage seems so cheap when you're buying in small quantities, it is surprising in the beginning to even think that storage is expensive. But when you talk to these really large-scale storage system operators, they'll tell you that that is the main cost, because as the size scales, it quickly becomes millions of dollars just for the hard disk space. Right? So the storage might seem cheap, but for large-scale systems, that is one of the main expenses. And then, as we discussed earlier, it leads to other expenses like energy, cooling, physical space, operations, and so on. The second important resource is disk I/O bandwidth, which is basically how much amount of data that you read and write from hard disks. So as the technologies for hard disks are evolving, the amount of data, that is the storage size for hard disks, is increasing, like from 2 terabytes to 8 terabytes to like 16 terabytes and so on and so forth. But the I/O bandwidth is not increasing as much. So basically, disks are becoming fatter and fatter, but the pipe to read out the data is not becoming fatter. So you can think of it now, let's say when one disk fails, previously just 2 terabytes used to fail and you had to reconstruct that. But now you have 8 terabytes or 16 terabytes failing, but still the speed at which you can read out from other hard disks is the same. So you're just going to take longer and longer to reconstruct from a single failure. So this becomes more and more of a problem as disk gets fatter and fatter. So disk I/O bandwidth is another scarce resource, and storage system operators are always trying to optimize for. Another important resource is network bandwidth. So basically the servers on which disks are put in are connected through the network, and this typically has a hierarchical structure, as I'll come to briefly a little bit later. There's basically what are called racks and aggregation switches, and basically as we go higher in the hierarchy, the cost is higher because there is what is called an oversubscription factor. That is, the bandwidth is allocated less in terms of the proportion to what is there at the lower level. So it will be more clear when I go to a picture later. But basically, so network bandwidth is also a key resource. So given these resources, when we are looking at codes for storage, there are some key metrics that we will want to watch out for. Right? One is space overhead. Right? In order to store one logical unit of data, how much actual physical space that you're going to consume, right? And in my conversations with the operators and administrators of large-scale storage systems, in some of the enterprises which have really large-scale systems, including Google, Microsoft, Amazon, and Facebook, they tell that even single-digit percentage reduction in storage space, 5%, 6%, which might seem small, is significant to them because it translates to millions of dollars in reduction in cost, which is good news, right? Because for coding theorists, there is a role to play in terms of reducing the storage space if we can maintain the same properties while reducing the storage space. And second important metric is read latency. So basically, these storage systems need to meet certain kind of requirements from the higher levels, which basically interact with the storage systems through reads and writes. And typically, many of the systems which do data analysis and so forth have immutable data in the sense that read latency matters more, and typically they ingest data in writes and read. Sometimes the write latency also matters, but here I'm mainly pointing out read latency. So these requirements are typically specified in terms of what are called service level agreements or service level objectives, depending on whether it's a strict requirement or just an objective. In fact, many of the systems, like cloud storage systems, have to pay back money to the customers if they don't meet these requirements. So it's very critical for them. And when looking at read latency, there are two kinds of reads to keep in mind. One is normal reads, meaning that a read request comes in for a chunk of data, and that chunk of data is available in your system. You just go to the location and you read. That's a normal read. The other type of read is what is called a degraded read. So degraded read is basically read for a unit of data which is missing. That is basically maybe a hard disk has just failed and the data unit was stored on that. Right? So this is a degraded read, and now in order to serve such read request, you have to reconstruct that data on the fly, right? Because we have added some redundancy, so we better be able to reconstruct it and serve that request. So here, these requests typically, obviously, will have longer time, right? So because you have to reconstruct it, and they translate to tail latency. Basically, tail latency are like if you look at the read latency of all the requests in a day, and you are sorted according the ascending or descending order, and basically whatever are the higher values, they fall at the tail. So you look at 99th or 99.99 percentile, and they look at what is the latency. And these service level agreements and objectives that I mentioned earlier are specified in terms of these percentiles. At 95th percentile, you cannot be more than X milliseconds, and so forth. Okay, so that is why this reconstruction, that is reconstructing the data that is missing, is so important, and how much time it takes and how much resource it takes matters a lot. Okay, and also as we saw earlier, we also want to keep track of disk I/O bandwidth consumption, right? Because it's a scarce resource. This is basically just the amount of data read and written from the disks. And the other one that we saw as we saw, so this is also a metric we want to keep in mind, which is network bandwidth. And as I was mentioning earlier, so this is the picture where typically data centers are architected in this kind of an hierarchical fashion where you have servers, which is down here, these boxes, and then they are connected to what is called a top-of-rack switch. And then these are connected to higher level switches, typically called aggregation switches or routers. And I was mentioning about oversubscription. So basically what that means is at the link down here, so this could be, for example, 1 Gbps network link. And you could have, let's say, 40 servers under one top-of-rack switch. But the bandwidth for the link that is going out of this top-of-rack switch can be only 10 gigabits per second. So if all the servers communicate at the maximum possible speed, you should be able to handle 40 Gbps, but it won't be there. So it will be only 10. So as you go higher and higher, there is this oversubscription. So here it is 4:1, right? So there's that kind of an oversubscription. So that's why, so kind of, we want to keep track of network bandwidth with placing more premium on kind of higher level links. Okay, so these are the metrics that we will keep in mind. Now, as we saw earlier, as I was mentioning, failures and unavailabilities are the norm rather than the exception, even in these large-scale storage systems. And the main reasons are that the first one is that they are built out of commodity components for economical reasons. So decades ago, the design of large-scale systems moved from highly reliable mainframe, the kind of systems, to commodity warehouse style kind of computing and storage. So each component is failure prone, and the resilience is handled at the software layer. And in addition to this, there are many other issues like software issues, power failures, maintenance, and so many other reasons due to which some part or the other of the system may be down. It might be a failure or it might be just unavailable. And if it is unavailable for longer than certain amount of time, it's kind of equivalent as failure as far as the system is concerned, because as we saw earlier, this latency aspects kick in and you cannot just wait for hours or days for the data to come back. So in order to provide resilience to storage systems, data has to be stored in a redundant way. So traditional approach, let's say a few decades ago when storage systems were small, was to just replicate the data, that is to have multiple copies of the data. So for example, 3x replication used to be the industry standard. And in this case, let's see a quick example. So we have 4 data blocks here, A, B, C, and D. And under 3 replication, 3 copies of each of these blocks are created, and then they are distributed across different disks or placed on different servers. So here I'm showing as servers, and sometimes in some enterprises, they can even address like particular disks, and it can go to particular disks. Okay, so now this replication strategy was fine when the size of the systems were small, but this high overhead is not sustainable for really large scale systems of today. So key to kind of scale these storage systems is to introduce resource efficient fault tolerance, and this is where Erasure codes come in because they provide a storage efficient alternative to replication. So let's take a quick example to see exactly how Erasure codes fit in to the storage systems. So on the left here, you see this 3 replication scheme that we just saw. So we have 2 data blocks A and B, and the goal here is to tolerate any 2 failures. So we can achieve it by replicating it 3 times, right? Because if any 2 blocks are failed, even if it is that the 2 copies of the same block has failed, we still have another copy, so data is not lost and we can recover. So here the storage overhead is 3x, right? 3 replication. Now on the right, you see n equal to 4, k equal to 2 erasure code. So 2 is the size of the message, so we have 2 data blocks. And n is 4, that is the length of the code word. So we have in total 4 blocks, right? So now you should think of this code as running byte-wise across the blocks. So you take first byte from block 1, first byte from block 2, and then create the first byte for block 3, and then create the first byte for block 4. Right? So that's like your code. So think of it like in bits also, that's fine. Right? So that is how we can create these blocks 3 and 4. So these are called parity blocks, by the way. So data blocks and parity blocks. So in this code, storage overhead is 2x, only 2x as compared to 3x for 3 replication, but it can still tolerate 2 failures, right? So for example, if the same first 2 blocks have failed, we can still decode the data. Why? Louder. You all don't have the mic. Yeah, so we have 2 equations in 2 variables, and those are linearly independent. So these parities would have been designed in such a way that they are linearly independent so that you can solve for it and we are fine, right? So in general, so this was just an example, in general it is well known that erasure codes require significantly less storage overhead in order to provide desired fault tolerance. And for this reason, many large-scale storage systems, including those employed at Facebook, Google, Microsoft, Amazon, and any large company that you can think of, uses erasure coding in their storage systems. And here is a quote from Cloudera, which is maintains Apache Hadoop, which is a big data storage and analysis platform widely used in industry, quoting that erasure coding in HDFS, which is Hadoop distributed file system, their distributed storage layer of the stack, that erasure coding is going to be an important feature in years to come. That's because now data is so large that almost every enterprise, every user wants to use coded storage. So cannot afford to have multiple copies of the data. Okay, so now just recall one point that we had seen earlier in the primer of MDS codes, that is maximum distance separable codes, right? So recall that they require, for a given amount of fault tolerance that you need, they'll consume minimum storage overhead, or vice versa, that is for a particular amount of storage overhead, they give you the maximum fault tolerance. And that in an NK MDS code, you can tolerate any n minus k erasures, right? And Reed-Solomon is the popular example. So now let's see how coded blocks map to storage systems. So I'll take this example of n equal to 14, k is equal to 10, because these are the parameters in published works from Facebook, the parameters used in their storage system, at least in the published papers. So since k is 10, we will take 10 data blocks. And then n is 14, so we have 4 parities, right? So these P1 to P4 are the 4 parities. And these parity blocks are computed. So if you're using a Reed-Solomon code, then you would be computing it using the Reed-Solomon code. And then these 14 blocks are stored on different disks. And typically these disks are chosen across what are called failure domains. That is, so that when some number of disks fail, so these failure domains are like where the correlated failures could be there, like in the question, right? So then you don't want to have multiple blocks within that failure domain, because then you'll have multiple simultaneous failures, right? So typically they handle those kind of correlated failures by placing each of these blocks on a separate failure domains. Otherwise, the storage overhead needed would be higher. So typically these failure domains are, racks, as we saw in that picture. So everything under a top of rack switch, because if top of rack switch fails, it might take a long time to get access to any of the disks within that. And also this kind of, there are power domains in a data center and so on. So one notation to keep in mind, yeah, go ahead. Oh, so the alphabet size typically that is used is 256, which is 2 to the 8. So basically you'd use 1 byte to represent one symbol. For everybody, like here for simplicity, we assumed ZQ as the finite field size, right? But typically what is employed in practice is a more sophisticated finite field where Q doesn't have to be prime, it can be power of prime, and typically 2 to some power is used because then you can represent and implement more efficiently. So 2 to the 8 is the field size that is typically used. And that was what was published too in Facebook and even other companies, yeah. Any other questions? Okay, cool. So one notation that we will keep in mind is what is called a stripe. So these 14 blocks are in general n blocks corresponding to this one set of k data blocks is called a stripe, because that's kind of an independent entity. And when we are looking at codes, right, so often it's sufficient to look at this stripe at a time. And as we will see, sometimes you need more, but stripe is a term that I will use throughout the talk. Okay, so now classical MDS codes have been around for decades, and they have been used in various type of applications like point-to-point communication and also local storage in computers, for example, in RAID systems. So RAID stands for redundant array of independent or sometimes also inexpensive disks. And almost every disk system uses RAID within, that is locally. Okay, so that uses, they started out with this single parity check code where you would have a parity unit for each of some k data units. And then as disks started failing more, or as disks became fatter, as I was mentioning, but the read bandwidth was still the same, then there were schemes which using 2 parities and not just 1 and so on. So codes have been used from decades. But their recent application in this new domain of distributed and large-scale storage systems has brought new challenges to these versatile tools. And these new challenges are due to this large-scale, distributed, and new modes of operation. And there are 2 challenges or problems that we will look at. First one is the reconstruction problem. So what is the reconstruction problem? So in classical MDS codes, we saw that they are optimal in utilizing the storage space, right? Because they are an MDS, and MDS means that they can tolerate any n minus k, and that's the maximum one can do, right? But they result in increased usage of other cluster resources. We saw it's not just storage, so there are these other metrics that are important, right? And we'll see why that is the case, and especially during reconstruction. So in replication world, which is on the left, let's say some block is lost or unavailable, we can recover it, reconstruct it by just reading from its replica, right? Because we have a replica. So under replication, the amount of data read from disks when doing reconstruction is equal to the amount of data that is missing. Similarly, the amount of data that is transferred across the network is equal to the amount of data that is missing, right? And also, the number of blocks that you touch when what you have to access is also equal to the number of blocks that are missing. So here, one block is missing, and we read from another block. So you are going to access only one other disk, right? However, if we go to the Erasure coded version that we had, where we had a n equal to 4, k equal to 2 code, So here, if the same block is missing, there's no replica, right? So in order to reconstruct this block, now we have to decode. So in this particular example, in order to reconstruct A, we have to read some two other blocks. It's in the classical MDS case, it's equivalent to decoding fully. So basically, we have to read two other blocks, and then in this case, we have B and A plus B. Then you subtract B from A plus B and get back A. So in this case, the amount of data that we are reading from the disk is twice the amount of data that is missing. Similarly, the amount of data that is transferred across the network is twice, and the number of disks that we are accessing is twice. Right? So in general, if we look at both replication and coding, whenever we have an NK classical MDS code, all these costs are k-fold. K-fold amount of data read, k-fold amount of data transferred, and k-fold access. So this is a big problem. Why? Because first of all, it increases the disk I/O and network bandwidth usage, which are important metrics, right? And secondly, it worsens the latency of degraded reads. We saw that degraded reads require reconstruction on the fly. So if we are reading more data from the disks, if we are accessing more disks, all this is going to take more time. So it worsens the degraded read latency, right? So which means basically tail latency is going to increase. And this is one of the main concerns that operators have in mind, that they might miss the service level agreements, which is detrimental for them. So in fact, many of the cluster operators consider these as a major concern in erasure coded storage systems. And another aspect it affects storage systems is that it increases repair times. So basically, in order to repair a failed disk, or if a server has failed, all the disks within it, they're going to take longer, and this affects the entire system reliability, because typically you model or think about this reliability of the entire system using like a Markov chain, where the time taken to repair plays an important role. And if you take longer to repair, the entire availability of the system comes down. Okay, so this is the reason why reconstruction in erasure coded storage systems is a problem when classical MDS codes are used. So just to show you some real world numbers. So we'll go back to Facebook's storage system. In fact, I'm showing these numbers because I collaborated personally with Facebook folks, and I did these experiments to measure, so I have some data to show. So here, for these n equal to 14 and k is equal to 10, recall there is this k-fold overhead, right, in terms of amount of data read, transferred, and number of blocks accessed. So here it is 10-fold, right, because k is 10. And so this, the plot that I'm going to show is coming from a storage system that has multiple tens of petabytes of Reed-Solomon encoded data. So on the y-axis, we have the amount of data that is read and transferred just for reconstruction of Reed-Solomon encoded data. Okay? And on the x-axis is date. That is like for every day, there is a number. And you're seeing the amount of data transferred and read every day just for reconstruction of Reed-Solomon encoded data in the system. So roughly, we observed a median of 180 terabytes of data and maximum up to 250 terabytes of data transferred across the network and read from the disks solely for reconstruction of Reed-Solomon encoded data. Okay, so I just wanted to show this to see that this is a real problem. Failures are common, and these operations keep going on all the time. Reconstruction operations keep going on all the time in the systems. Yeah. Good question. So in this classical MDS code, when you're doing this recovery of one symbol, you have no choice. You're just decoding everything. But we don't need those symbols. right? So we have only one block missing. So let's say there is a read request for that block. Like I don't care whether if you give me other blocks or not because I don't need it, right? So similarly, when one disk has failed, all other data is there in the system. We don't have to decode it. But classical MDS codes kind of force us to decode everything, and that's where the cost is coming from. No, right? So if you're thinking about these blocks, there could be read requests for only some part within the blocks, right? And the way to think about it is, so you have these blocks, right? So I'll go back to the case where we had just 2 data blocks. So then it could be a file that is split into 2 parts. So you have one single file, and then it is split into 2. And the read request could be just for some part of this block, or it could be only for the first block. So even typically, actually, in systems like Hadoop, which is a data analysis system, and Hadoop distributed file system is the underlying storage layer, there are what are called map tasks, which are some kind of tasks that are run. They all operate at the block level. So one task operates on this block, another task operates on this block, and so on. And there's kind of each reader is reading only one block. Right? So this is just one example where a particular reader is not reading the entire file. Right? And the encoding now, what happens is, suppose we come here. This is block 1 and block 2. Then encoding basically is like taking this as M0, taking this as M1, and then generating the first parity here. So if this was just XOR, then this would be XOR of this. Right? So if this block is missing, I need only this part. I don't need this block. Okay, so that is the key difference between the classical decoding and the reconstruction. Sorry. Okay, cool. So now, in reconstruction, within the reconstruction problem, so there are 2 flavors of the problem corresponding to 2 different metrics that come into play in real-world systems. The first one is reconstruction bandwidth, which concerns with the use, that is the amount of network bandwidth consumed and the amount of disk I/O bandwidth consumed during reconstruction. So I want to just make one note here. So it's important to note that the disk I/O bandwidth consumed and the network bandwidth consumed need not be the same, because each server, right, so or this disk can read the data and do some computations and send smaller amount of data over the network. Right, so because there is some computation capability at the servers, even at disk level. Right? Typically, you have multiple disks within a server, and server can do some computations. So different models for this problem has considered these different flavors. Right? So basically, we always have this inequality that disk I/O bandwidth is greater than or equal to the network I/O bandwidth, because whatever you are sending has to be read. Right? So that is why you have disk I/O bandwidth greater than or equal to network bandwidth, but sometimes in some code constructions, which we will not have time to go into, both are matched. Okay, so this domain of what is called regenerating codes, introduced in the seminal work by Dimakis et al., addresses this problem, that is looking at the bandwidth problem for reconstruction. Okay? So we will get into a little bit more detail of what it is and the kind of impact that it has had. Second one is reconstruction degree. So this is another aspect that is important. So here, what are called local repair codes and other ensuing works, so introduced by this seminal work by Gopalan et al., addresses this reconstruction degree, which is basically just the number of nodes you access, not the amount of data you're reading, just the number of nodes you access, during reconstruction. We will see that why it matters. And in the literature, there have been many different names, local reconstruction codes, locally repairable codes, and so on. But good thing is that they all have this short form of LRC. So we will just use LRC so that we are covering all of those. Okay, so just brief overview of each of these two problems. One is the reconstruction bandwidth, right? So the key question there is, can we have the storage efficiency and reliability of classical MDS codes while reducing the bandwidth consumed during reconstruction, right? So bandwidth efficiency of replication and storage efficiency of classical MDS codes. And the answer turns out to be, as shown by this seminal work by Demarcus et al., is that almost, but there exists a trade-off between the two. And regenerating codes are basically codes that are optimal with respect to this trade-off. So I'll not go into the details, but take an example to show what are the key differences between regenerating codes and classical MDS codes and why they are able to reduce bandwidth, okay, while still maintaining storage efficiency as MDS codes. Just a note on that there are various flavors of regenerating codes. Some of them are not MDS, but the surprising ones, at least to me, are the ones that are still MDS, but are able to reduce bandwidth while still being MDS. Okay, so let's take this same example that we have been seeing, right, for the classical MDS code. We have A, B, A plus B, and A plus 2B. Now, if A is failed, as we have seen, we can connect to any two blocks and decode, right? So now just consider each node, now instead of having one symbol, has two symbols, but the code is still the same, right? So as I was mentioning earlier, this is how it is encoded anyway. You take one symbol each from each block and you encode, and that is what is being shown here, but just that the smallest instance of the problem that we are considering is now has two symbols in each node, but we are still encoding the same way, so nothing has changed when this first block has failed. So now keep in mind that when first block fails, both the symbols fail. The overhead would still be 2x, because for each of those sub-units, you have to access two symbols. So the total you will be accessing 4 symbols to recover 2 symbols, so the overhead is still 2x, right? But now, consider this example where these parity symbols have changed, so they are encoded differently. So now, one thing that, note that the parities for these two columns, if you will, now those are coupled together, right? So both the parities now are functions of these 4 data blocks. So now in this code, when the first block fails, that is when A and C are missing, we can reconstruct using only 3 symbols instead of 4. So basically, you can read the first symbol from each of these remaining 3 nodes. And you can subtract. So the first symbol is B, so we can subtract out B from the other 2 symbols. And that gives us 2 linearly independent equations in A and C, which are the 2 symbols that are missing. And so you can decode A and C, right? So classical MDS code required 4 symbols, whereas this code requires only 3 symbols. So you can easily check that this code is still MDS, that is, you can tolerate any 2 failures. So it has retained the MDS properties, storage efficiency, fault tolerance is the same, but the reconstruction bandwidth has reduced, right? Okay, so this provides 25% savings in the network bandwidth, right? And it is for this particular parameters, and the savings that can be achieved in general is much larger, but while retaining same reliability as classical MDS codes. So mainly, what are the key aspects that helped in reducing the reconstruction bandwidth? So one is that we went from scalar codes to vector codes, in the sense that instead of looking at each node being as a single symbol, now we started looking at it as a vector, right? So we needed two symbols, right? So we expanded horizontally, right? So this has a trade-off, which is basically computational complexity increases. So that is the trade-off. But typically, that's a good trade-off to make in storage systems, that there is computational complexity available if storage space can be reduced, or if these other resources like disk I/O or network bandwidth can be reduced, then that can be used. And the second important difference was here, instead of connecting to 2 nodes during reconstruction, we are reading from 3, right? So that cost has increased. So reading from 3 instead of 2, and that also turns out to be necessary. If in regenerating codes, you need this degree, which is typically denoted by D, to be greater than K in order to be able to reduce the bandwidth. Okay, and there is beautiful theory on this, on the model for regenerating codes, and exact characterization of the trade-off by Dimakis et al., and a large body of work ensuing after that work, including my own and several others. And of course, I'll not be able to cover all of them in detail, and I've put them all here and be sharing the slides. And this is still, not everything. There are a lot of other works, and I would encourage you to go and look at these references if you're interested, and references therein, and works that cite these works, and so on. There's really a large body of work on this. Okay, so now very quickly on the second problem in reconstruction, which is this reconstruction degree, right? Which was basically the number of nodes or blocks you access during reconstruction. So in the classical NKMDS codes, we needed to connect to how many? To decode, to reconstruct one block that is missing. K, right? Because they don't distinguish between this kind of partial reconstruction or full decoding. So degree is K, right? And in regenerating codes, which helped us reduce the reconstruction bandwidth, the degree was greater than K, right? As we saw, that was one of the key ingredients in reducing the reconstruction bandwidth. But it turns out that in some applications, this higher reconstruction degree matters, and it is worse if it is higher. Like for example, in storage systems, there are different sizes of reads. Some systems might have small read requests, and other systems or applications might have larger read requests. So when the read request sizes are large, then the bottleneck is typically just the disk I/O bandwidth where you're reading from, or the network bandwidth if it is congested. So typically bandwidth of some sort is the bottleneck when the read sizes are large. Because the time to connect to disks or servers, or that initial latency, gets masked out by the amount of time it takes because of the bandwidth to read that. But when the read request sizes are small, the bottleneck is this initial time, the latency to connect or read. So the bandwidth, that is how much time it takes to actually read, will be small. And hence this initial setup cost, if you will, that will become a key factor. And hence, in systems with small read request sizes, this reconstruction degree becomes an important factor because that increases latency. And often, when you have to connect to more, there are higher chances of what are called stragglers, which is basically in this kind of large-scale systems. For some reason or the other, some servers will be slow to respond. Some disks will be slow to respond, for queuing and so on, for various reasons. And hence, just by having to need to connect to more, increases the chance of having some stragglers. And typically, you'll have, if you connect to 10, typically one of them will straggle. And that way, just by needing to connect to more, increases the latency. Okay. So that is why for some applications, there is interest to reduce the reconstruction degree. Okay? And this was looked at by, the theoretical formulation for this problem was looked at by the seminal work by Gopalan et al. and many other works that followed after that. So the first question is to think is whether it is possible to reduce the reconstruction degree at all. So far we haven't seen any trace of that. We had k or more than k, right? So can we go less than k? So the answer turns out to be yes, as was studied in this paper, and also one or two papers more from code design or systems perspective that looked at this problem had also considered. So these codes are called local repair codes, and as I mentioned, there are several other names, but we will stick with just LRC so that we are covering all of them. Okay, so let's take an example to see what is the key idea that enables to go below k for reconstruction degree. So recall this 1410 Reed-Solomon code or classical MDS code, right? So we have this 10 data blocks, 4 parity blocks, and now one need to, when we are looking at reducing the degree, so we will take a closer look at the composition of these parities, okay? So in this classical MDS codes, these parities that we have we can call them as global parities because they are functions of all the message symbols. And it's kind of necessary for MDS codes because recall that nk MDS code can tolerate any n minus k failures, right? So every parity symbol better have something about each of the message symbols, right? Because any of the message symbols can be missing, and k of them, n minus k of them can be missing, and then the n minus k parities need to give us n minus k linearly independent equations in those missing message symbols, right? So thus, every one of those parities in MDS codes need to be functions. So they have to have some component, some information about each of those message symbols. So these are called global parities, and if it's a linear code, and typically almost all codes used in storage systems are linear, basically we will have linear combinations of the message symbols. So the key idea in going lower or reducing the reconstruction degree is to have parities which are functions of smaller subset of the message symbols. So in this example, now we will have two new parities which are denoted by L1 and L2. Now these are linear combinations of only 5 of the message symbols. So L1 is linear combination of only first 5 and L2 is linear combination of only the second 5. And G3 and G4 are the global parities as we saw earlier. They are still linear combinations of all. But we have reduced the total number of these global parities and used some of their space to add these local ones. Okay, so these are called local parities because they are more local in terms of these message symbols. So here in this example, it is said that the locality is 5 because if any of the message symbols are missing, then you can reconstruct them with reconstruction degree just 5, not 10, right? So we have half the reconstruction degree. So k to k over 2 if we add two local parities. So a bit of subtlety in this notation is this is actually called what is called information locality being 5 because here we are looking at only information or these message symbols reconstruction, right? So if parity is missing, I would still need 10 to reconstruct if the global parities are missing. So we are not covering all blocks with this locality 5. One could do that. There are code constructions looking at all symbol locality, which means that if any symbol is missing, you can reconstruct with this lower degree. Okay? So basically local parities help in reducing the reconstruction degree. That is, you can reconstruct by accessing to fewer data blocks. Right? And then global parities serve the same role as before. Basically, they help they come into play during catastrophic failures in the sense that let's say if more than one block is missing, then the local parities cannot help. Right? So let's say within these local blocks, if 2 are missing, then it won't help because we have only a single parity within that local part. So that is when the global parity will be used. But one key thing to keep in mind that these codes are not MDS. And this MDS property and local reconstruction properties are in conflict. As we saw that if you want MDS, every parity has to be a function of all the KMSS symbols, and if every parity is a function of all KMSS symbols, we cannot have lower reconstruction degree. So these local LRCs, basically all these kind of local codes trade off in terms of storage space optimality in order to reduce reconstruction degree. So they are not MDS. Again, like in regenerating codes, there is a large body of work on local codes. So I won't be able to cover all of them, but I've made an attempt to include some of them here. But again, there are a lot more than these. So if you're interested, go and look at these, but also the references in these and the works that refer to these works and so on. So before I end this reconstruction problem part, I do want to mention the industry impact that the works from the coding theory community has been able to make in both of these, reconstruction bandwidth and reconstruction degree problems. So the first one I would like to mention is piggyback codes, which I was a part of too, which looked at optimizing reconstruction bandwidth, both disk I/O and network bandwidth. So this was incorporated into Apache Hadoop distributed file system. So their latest version, which is 3.0, where they introduced Erasure coding, has piggyback codes as one of the options in them. And Apache Hadoop is one of the most widely used data storage and analytics platforms in the industry. So, so now the piggyback codes are available in their storage stack. And piggyback codes were also independently implemented by NetApp and Cisco. So I had worked with Facebook, and I had implemented it on their internal system. So they had an internal version of HDFS, but the, excuse me, but the outside, mainly the open source of the Apache version, as it is called, is very different. And then Intel and Cloudera engineers helped in porting this into the Apache version. Okay, so another class of codes which have been incorporated into real-world systems is what are called clay codes. And this has been incorporated into a system called Ceph, which is also a widely used distributed storage system. And it is widely used especially in the scientific computing community. Okay, so like there is a community called high performance computing, like in CERN labs, if you've heard, they all typically dominantly use Ceph file system. Clay codes also are kind of regenerating codes, and they optimize for bandwidth. And the third one I want to mention is going into the reconstruction degree now. Basically, LRC codes, they in fact, this work, the Gopalan et al. Work and the other works, a fraction of those works actually came out of Microsoft research and Microsoft. And these codes are actually employed in Microsoft's Azure storage system. They're the base for their cloud storage system. Okay, so this, as you can see, completely theoretically sounding works have had real-world industry impact. Right? So this is inspiring. Okay, so now with that, we will go on to this second problem, which is the code conversion problem. So, Nikhil, so I'm fine taking a break at 11:30 to let's go with that, right? Yeah, okay, yeah. Cool, so any question on this before we go to this? So I'll just have to switch back. Okay, so now for this code conversion, problem. So in order to understand what the problem is, so let's start taking a look at how redundancy is configured in storage systems. Excuse me. Okay, so basically redundancy in storage systems is chosen in order to meet durability and excuse me, availability requirements. So durability is quantified in using various metrics, and typically what is used is mean time to data loss. So that comes from modeling the system as a Markov chain and then finding the mean time to data loss, right? You might have worked out such problems if you studied Markov chains, but it's not needed to understand this part of the tutorial. And then availability requirements are specified in terms of some kind of constraints on reconstruction, as we saw, because availability basically means that when read requests come in, you have to be able to serve, right? So that means that when degraded reads come in, that is read requests for unavailable data units, you will specify some kind of constraint on how quickly you're able to respond to those. So availability typically comes in the form of restrictions or some constraints on reconstruction. And both of these, for both of these requirements, so typically some kind of an assumption or like some informed assumption is made on the failure rate of the disk population, like an average across the disk fleet is made. So basically this choice of the parameters n and k are made in a top-down fashion with some average understanding of the failure rate. So implicitly what is assumed is that all disks kind of fail similarly, and hence we can choose the redundancy parameters based on this durability and availability requirements for all the disks in a similar way, right? So we can call these the current approaches. Those are agnostic to the differences in failure rates of the various disks, and there are differences, as I'll just show. So we did a study on the failure data from a company called Backblaze, which is a data backup company. And we observed that failure rates vary significantly, and I'll briefly touch upon this data soon. But in terms of what we observed, failure rates vary significantly, and in this plot, y-axis is what is called annualized failure rate, which is basically what fraction of the disks are expected to fail in 1 year. And on the x-axis are different disk groups. So here we've chosen like different make models as groups, right? So there are significant differences. And also it is well known that the failure rate of disk groups vary over time as disks age. So initially there is what is called infancy. It's like infant mortality, which is there in many kind of mechanical instruments. So the failure rate is initially high, and after some time it enters into a period what is called useful life period, where this failure rate is pretty stable and pretty low. And then after some time, again the failure rate increases, and that is called as wear out or old age. Okay. So briefly about the data. So this is from production cluster at Backblaze, which is a data backup company. And here were the make models of the disks, which had significant number of disks in it. That is basically roughly around or more than 10,000 disks. And this is reliability data from 2013 to 2019. So actually it's remarkable that this company actually makes this data available in open source. So any one of you, if you're interested, can go and analyze this data. Okay, and so these were the 7 make models that we used in our analysis. So previously I showed you a textbook AFR versus time plot, and that's called a bathtub curve because it looks like a bathtub, right? So initially high, then pretty low and stable, and then again high. So this is a real world bathtub curve, right? So this is for one of the disk make models that we saw. Again, y-axis, here it is cumulative AFR, and y-axis is again age. And here also we can see roughly it takes a bathtub shape, and there is infancy, useful life, and wear out. Right. Okay, so basically, although the configuration approaches, redundancy configuration approaches are implicitly assuming that disks fail similarly, right? So under this assumption, different stripes, recall that a stripe is the set of blocks, data and parity, which belong to like one group. So under this implicit assumption of all disks failing similarly, different stripes have, with same parameters, have same reliability, right? Because all disks are implicitly assumed to be failing with the same rate. So if you have same redundancy, you get same reliability. But however, as we saw in the real world, it's not so. Different disks fail differently, right? So the picture is very different. And in this different picture, different stripes that have same amount of redundancy can have very different reliability, right? So some of the stripes with a certain amount of redundancy might have less coverage than what the administrator thought of, right? Because it might be insufficient because of the failure rate differences. And for some other stripes, it could be that the redundancy provided is an overkill, right? So because the failure rates of the particular disks where that stripe got saved on was lower, right? So it's not clear. And in fact, this is where it turns out to be wasteful, because most of the time, operators will have to be over conservative and provide more than necessary redundancy for some of the stripes. And this was the opportunity that we explored in one of the systems works that we did. I will have a reference to that. Basically, we made a case for tailoring the redundancy for the disks where it gets stored, right? So kind of tailor it by performing an online monitoring system, and then tailor the redundancy depending on where the stripes get stored. And the main opportunity to tailor the redundancy is during the useful life period, right? Because it's highly variable, or at least that's the easiest first thing to do, right? Because the failure rate is stable and pretty low during useful life period. And then if we can lower the redundancy during that period, we can provide storage cost savings, right? So what would this mean? So this would mean that suppose we have a storage system with different disk groups, let's say X and Y, then these different disk groups are going to be deployed into the system at different time instance. And then each of them is going to have a different bathtub curve. So they are going to enter useful life at different time, exit useful life at different times, and so on. So kind of one needs to keep track of them. And during the useful life and the wear out stages, we propose to use the default approach and then tailor the redundancy specifically to that failure rate of that group during the useful life period. So in order to do this, what does one has to do? So one is that we need to know when to change the redundancy, that is when the disk groups enter and exit useful life, and what redundancy to use, because that has to be dependent on the failure rate during the useful life period, and also how to do these transitions when you convert from default approach to this specific approach and then come back to the default approach. Okay, so this is what we looked at in a work that was published in Usenix FAST, which is a storage systems conference last year. So basically, we looked at heterogeneity-aware redundancy tuning, or HART for short. So basically, HART actively engages with the disk bathtub curves by monitoring the failure data and then identifies when the transitions occur and basically suggests what scheme to use depending on the observed failure rate. So these all have to happen on the fly in production. You have to observe and then change, right? So basically, HART takes in two inputs, which is the reliability requirement. So it could be anything, but we are working with mean time to data loss. And also the disk health monitoring data. So most large-scale storage systems already have pretty extensive disk health monitoring system in place, as you can imagine, right? Because they need to be able to do a lot of operations on it. It's just that that data is not being used as effectively as it can be. So then HART consists of three main components. So the first one is an anomaly detector. So I won't have time to go into the details of it. I would encourage you to read our Usenix fast paper if you're interested. But basically it turns out that many a times you'll have spikes of failure rates for various reasons. One is this correlated failures, for example, right? Due to which you will see a large number of disks, like hundreds of disks failing within a very short period of time. So if we just use that to estimate the failure rate, then it will be like a huge spike and disks will exit useful life very quickly. However, we don't have to worry about those kind of failure rates because those are handled in fact kind of has to be handled with different approaches, like how I was mentioning earlier, by placing them in different failure domains, because cannot really handle hundreds of disks failing by adding redundancy, which meaning that you would need to have huge amount of redundancy. So those kind of are handled separately by placing each of those blocks of a stripe in different failure domains, so that even though hundreds of disks are failing at a time, we will not have all the blocks failing in a stripe. So in a stripe, you will still see just one block missing, right? So that is why we have to filter out such things which we shouldn't take into account when tailoring the redundancy. What we have to take into account is inherently the failure rate of the disks changing because of old age or some other reason. So there are many other reasons like temperature and other aspects also which kind of change the failure rates of disks. Okay, so the second one is, the component it has is called what is called the as change point detector. We are actually using off-the-shelf approaches in this work to do all of this. So change point detector just basically identifies those transition points, and it works pretty well. So basically, you identify when it kind of becomes stable and also when it starts rising. So two change point detectors. And the third component is the redundancy tuner, just basically which identifies what is the redundancy to use depending on the mean time to data loss requirement, and also, as I mentioned earlier, reconstruction requirement. So there are many other constraints on the parameters that we can choose, especially, for example, on the value of k, because you don't want it to be too large, then reconstruction, because k is very closely related to the overhead for reconstruction, and hence there are some restrictions on what parameters one can use. So redundancy tuner just suggests what to use. Okay, so again, I won't have much time to go into the details of the systems part. If you're interested, please take a look at the Usenix fast paper. So I'll just show you one plot of how much space savings can be achieved using HART, that is doing this redundancy tuning. On the y-axis here is the storage space savings in percentage, and on the x-axis are these different disk groups. And here these numbers are basically if you tailor the redundancy to the observed failure rates during useful life period, then how much space savings can be achieved. And as we can see, this can lead to 11 to 16% of storage space savings by doing this redundancy tuning. And recall that I'd mentioned earlier that even a single digit reduction in terms of storage space savings percentage is huge. So this leads to significant potential for storage space reduction and hence cost reduction, and easily run into millions of dollars of savings. Yeah. So, okay, good question. So this is with respect to using just one scheme for all. And here in this plot, one scheme for all is n equal to 9, k equal to 6. Very good question. So basically that is one set of parameters which actually is published in one of the papers from Google as the parameters that they're using. But we have these plots and numbers for other parameters also in the paper, that is using some other baseline like I forget exactly the other parameters that we had, but basically these numbers would change for different baseline schemes. Very good question, thanks. Yeah. Any other questions? Yeah, so that happens in both the schemes. Basically, each block within a stripe is placed on different failure domains.
So, in a particular stripe, are all blocks on the same type of disks?
Good question. So, in our scheme, we keep track of these different disk groups and their failure rates, and all the blocks within a stripe do have to be placed on similar type of disks. So that is one of the constraints, additional constraints that get put on when doing this kind of redundancy tuning. That is, placement now is more restricted. Very good question again, yeah. And we do discuss about this a little bit in the paper. And on the systems side, as I mentioned in my group, we do research on systems front as well. That is one other, what's one direction that we are tackling. Basically, that is one significant constraint actually, placement, having to require to place within a particular set of groups, how we can overcome that. Yeah. Any other questions? Okay, cool. So now it looks like redundancy tuning is pretty useful and can lead to significant savings in storage cost, right? So then all systems should right away start doing it, right? But there is one concern that needs to be addressed before that can happen, because redundancy tuning is not free. So when this AFR of disk groups change, we need to change the rate of the code. That is, this n and k parameters of the code has to change. And what that means for a storage system is that data encoded using one type of code now has to be changed to be as though it's data encoded under this another code, right? And often, one needs to change both n and the k parameter. So one might think that we can keep the k fixed and just change n, because that allows us to vary the overhead, because that changes the rate, or in other words, redundancy, right? But often that doesn't work, because as I mentioned earlier, in addition to durability, there are also constraints on availability, which places restrictions on what is the value of k that we can use. So if the value of k could be chosen anything, then one could choose a large k and then have large n when you need high redundancy and a very small n, that is just have only a few parities when you want lower redundancy, that is when the failure rate is lower, right? But that is not allowed in the sense that we cannot choose very large k because of reconstruction restrictions. So when operating within all these constraints, often one will have to change both n and k in order to go close to the allowed amount of redundancy. Okay, so one default approach of changing n and k for an already encoded data would be to re-encode, which is basically reading all the data and then computing the new parities, right? So, but this approach is prohibitively high cost for conversion, because typically these disks are deployed in fairly large batches, and then they go through these different stages together. So basically, a large number of disks transition their AFR phases together, and hence the data stored on all of them will have to be converted. So this results in highly varying and very spiky disk I/O and network bandwidth consumption just for doing this conversion. So here is some data on this. So this plot is showing the amount of disk I/O bandwidth consumed solely for doing this conversion operation if one were to use HART on production disks. So this data is collected from the failure data is collected from the production clusters at Google. And if we were to use HART on this cluster, then this would be the IO consumed just for doing conversion. So as we can see, for weeks together, 100% of the cluster IO bandwidth is needed to do just conversion. Right? So this is just unacceptable. So no system is going to do code conversion and redundancy tuning if this is the cost. Right? So a key barrier for doing redundancy tuning and leveraging all the advantages that it can provide is being able to do this conversion of already encoded data from one code to another code in a resource efficient manner. So before jumping into this, we have to ask ourselves whether it is at all possible to do this, right? Whether the conversion cost can be reduced. Right? The answer turns out to be yes, as some of you have already seen and as some of others might guess. Right? So let's take this quick example. So suppose we are going from single parity check code, as we saw one example earlier, of dimension k. So k, which is the length of the message, is also called as the dimension, to a single parity check code again, but with dimension 2k. Okay, so the k is changing from k to 2k, but we still have single parity. So here are the two initial code words, which has k data blocks and one parity block. So empty blocks are data blocks and shaded blocks are parity blocks. Now in the final code word, that is after doing conversion, we want to have 2k data blocks, right, empty blocks, and then one shaded block, which is the parity block. So we can generate this single parity check parity block in the final code word by combining the two initial parity blocks that we have, right? Because those are XORs of the case, and then we want one final XOR, we can XOR those two. Right? So this is significantly better than re-encoding. Re-encoding would have required us to read 2k data blocks, and now we are reading only 2 blocks. Right? So this is good news that now we can actually do better than re-encoding. So there is motivation to study this further in a more formal way. Right, so here is the outline for just this code conversion part. As I mentioned earlier, I'm going in more detail for this because this is a brand new problem. We have just started exploring this, and there are a lot of open problems. So if you're interested, I would be happy to chat, or you can read our paper, which is now available. Okay, so I'll first give a brief description about convertible codes, which is a framework to study this code conversion process. And then I'll go into looking at lower bounds on a specific cost metric called the axis, which is like similar to the degree cost that we saw earlier, in different regimes. So we tackled it in a piecewise fashion, handled it in different degrees, regimes, and then we can handle all parameter regimes using that. Okay, so quickly, so let's now go into convertible codes framework. So recall that what we want to do is convert data that is encoded using an NI, KI, initial code CI into data encoded into a final code, which we denote by CF, which would be an NF, KF code. Okay? Yeah. Yeah, I think like continue a little bit and then stop. Yeah. Okay. So that the people can think over this during the break. Okay. So both of these codes, consider them as from the same finite field. So this is the initial assumption that we have made. And then one thing to keep in mind is that both the codes encode the same information. So keep in mind that if now this is in the coding theory world, but when we model a problem based on a real world problem, when we are modeling a theory problem, you want to always keep coming back to the systems world or the real world where the problem came from to make sure that the model accurately reflects what is happening, right? So time to time, we should keep coming back to make sure we are reflecting the real world well. So one thing to keep in mind is that when the disks transition, right, so the same data is stored, so you have to encode the same data. So the information encoded in the initial code and the final code is the same. It's just that how it is encoded is different, right? So the redundancy would be different. Okay, and as I mentioned earlier, we need to be able to handle changes in this parameter k, right? So we are going from ki to kf. And since we have to consider the same amount of information or this message symbols, so we handle it by considering LCM of ki and kf message symbols. So using these LCM of ki and kf message symbols, then we will be able to handle the same number of message symbols, both initial configuration and final configuration. Okay. So let M denote this message vector, which is of the size of LCM of ki and kf. So because we are considering LCM of ki and kf message symbols, and more importantly, since ki is changing, during conversion, what you need to keep in mind is that multiple code words in the initial configuration are being converted into a different number of multiple code words into the final configuration, right? So this need to consider the multiple code words is very different from the reconstruction problem that we saw earlier, for example, where we could just focus on one stripe, so to say, right? So we could just focus on one set of data blocks and one set of parity blocks, and the problem was completely defined within that. And then we could study the reconstruction problem and optimize it and design the code. But here, because k is changing, we have to consider multiple code words. So we need to consider multiple stripes at a time, even to capture the smallest instance of the problem. Okay, so we have NI-KI code going into NF-KF code, right? And so this is a good picture to keep in mind. We will have multiple initial code words. Empty blocks are data blocks, shaded blocks are parity blocks. And then we are going into multiple different final code words, right? So we have multiple code words both in the initial configuration, which is at the top, and final configuration, which is at the bottom. So we have precisely M over Ki code words in the initial configuration and M over Kf code words in the final configuration, right? And now, since we are having multiple code words, we need to know which message symbols get mapped to which code words, right? Because basically, code words are mapped to set of message symbols, right? Each set of message symbols have a particular code words. So in order to do that, in the framework, we introduce two partition functions. So the initial partition function map the message symbols to the initial code words, and similarly, a final partition function which maps the message symbols to the final code words. So basically what these partition functions give us is mapping from which message symbols in the initial code word get mapped to which message symbols in the final code word. So for example, one mapping could be like this, like mapping initial message symbols, which are empty boxes again, to the empty boxes in the final code words, which message symbols map may vary. So another valid mapping could be this. And how this is mapped matters, and it will affect the cost. Okay, so as we will see later. Okay, so we have initial code CI going into final code CF, and we have initial partition PI going into final partition PF. So one other element that we will need next is the conversion procedure. So basically, we'll denote it with T. So this conversion procedure takes input as a set of initial code words. So the notation here, C of M, is basically code word corresponding to message M under the code C. Okay, so C of M is a code word for message M under code C. So the conversion procedure takes this multiple set of code words in the initial configuration, the initial code words that we had, and it outputs the corresponding set of final code words, which are like after conversion. So now we'll have the final code word. So this conversion procedure basically helps in doing the conversion. So I'll just take a couple of more minutes and then complete this with an example, and then we can take a break. Okay. So for example, if we are going from a 3-2 code to a 5-3 code, okay, so here we have Ki is 2 and Kf is 3. So the LCM is 6, so we will consider 6 message symbols. An example of initial partition could be something like this, where we have AB encoded together, CD encoded together, and EF encoded together in the initial configuration. In the initial configuration case 2, right? And in the final configuration, case 3, so one valid partition is something like this, where ABC are encoded together, which belongs to like one code word, and DEF belong to another code word. And if the codes are systematic, and as I mentioned earlier, systematic codes, or maybe not this, I mentioned about linearity, yeah, sorry. So codes being systematic is a good assumption for storage systems because almost all codes employed in storage systems are systematic, because when you want to read, if, I should mention, so systematic codes are codes where you have the message symbols as is without encoded. For example, the single parity check code that we saw is systematic because the first 2 bits of the code words are message symbols themselves. So if you want to read data that is M0, you can directly read it. In general, codes need not be of this form. Each of these bits in the code word could be a linear combination. So all of them could be parities. And you can still have the fault tolerance properties and so on. But for storage systems, it's not that great because when you want to read, for every read you'll have to decode. Right? So typically that is why codes used in storage systems are systematic. So if the codes are systematic, then the conversion procedure would look like this. So we'll have 3 initial code words where the empty boxes are data box and shaded blocks are parity blocks, going into 2 final code words where k is 3. Right? Okay, so now putting it all together, we have NI, KI, NF, KF convertible codes, which consists of 3 components. First one is a pair of codes CI and CF, where CI is NI-KI code, CF is NF-KF code, and a pair of partitions PI and PF, which map message symbols to different code words, and a conversion procedure, which takes the set of initial code words and maps it, that is, converts it into a set of final code words. Right? So this is the formal definition of convertible codes. So let's take a break here, and then after the break, let's start looking at the cost of conversion, which is going to be the cost of this conversion procedure. When should